Hello, dear students. It has been known since ancient Greek times that the square root of 2 is an irrational number. But how? In this video, we will see that. Let's get started. Now, according to legend, Hippasus, one of the first students of the Pythagorean school, began his experiments immediately after the Pythagorean theorem was proven. For example, what kind of experiment did he do, let's say? Hippasus takes a triangle. But this triangle doesn't really fit for this purpose. Let me try to make it more suitable. I'll make it like an isosceles right triangle. This looks much better. Hippasus says, since we have something called the Pythagorean theorem, so he thinks if I call one side of this triangle 1, let this be a right triangle, and call the other side 1 as well, I wonder what this side will turn out to be. He asks himself this question and comes up with a proof. Of course, this is just a rumor. Did Hippasus really do something like this? It is even said that after proving this, he was drowned. Did something like this really happen? Of course, all of these are just rumors. But let's stick with the story anyway. Now, it's useful to talk about rational numbers here. For example, why are rational numbers represented by the letter Q? Because the Q here actually comes from the English word quotient. It means quotient. In fact, what is meant by Q here is ratio. In other words, we represent rational numbers with the letter Q, which is the initial of quotient. Why? Because all of these numbers can be written in the form of a ratio. What does it mean to be able to write them as a ratio? Let A and B be integers. They can be written as the ratio of A to B. So then, our Hippasus comes along, and since this spot here can be expressed as a rational number, that is in the form of a ratio, he puts a question mark here. After all, there are no other kinds of numbers. In other words, for the Pythagorean school, there are only numbers that can be written as ratios. They never considered any other kind of number. So then Hippasus says, let me write m over n here. Let me express it as a ratio. At this point, we can say one more thing about ratios. In space, actually, all ratios exist in their simplest form, right? For example, take the rational number 28 over 35. Actually, we don't really need such a number. When we simplify this, we can see that it's, for example, 4 over 5. And likewise, in rational numbers, both the numerator and denominator don't appear as even numbers at the same time. So, for example, let's do it like this. Let's say 8 over 20 for this one. Here, we see that both the numerator and denominator are even numbers. In fact, let's make this 22 instead. We see that these are even numbers. But what is there in the set? There is a simplified version of this, right? If we divide both sides by 2, for example, this becomes 4 over 11. So actually, all rational numbers, they exist within the set in their simplified form. In other words, their simplified versions, where neither the numerator nor the denominator is even, are present here. So this m over n also represents such a version. In other words, a number written as a simplified crystal clear ratio. In this case, I need to say the following. Both m and n cannot be even at the same time, because their simplified versions are written here. Great! Now let's continue with our proof. Now I'm applying the Pythagorean theorem. The square of 1 plus the square of 1 equals m squared over n squared. Equals 2. M squared over n squared? Nice. We're doing well. From here, I'm moving n squared over here as multiplication. Or rather, I'm multiplying both sides by n squared. 2n squared equals m squared. Now, at this point, I need to consider something. Here, what I consider as m squared is equal to 2n squared. Now, what can I say about 2n squared? Since the number here has 2 as a factor, the number written here is definitely an even number. So m squared is an even number. For the square of a number to be even, the number itself must also be even. So I can draw a conclusion from this. That means m is even. Since m is even and k is a natural number, I can express m here as 2k. I can express it as a multiple of 2. Good. We've understood that m is even. Now, all I have to do is substitute this value I found back here. Let's do that now. What is n squared? Equals, I'm substituting 2000 in place of m, the square of 2k. What does n squared equal? 4k squared. These cancel out. And I found something strange about n squared. n squared, it's equal to 2k squared. So what can I say about n squared from here? Since it's a number that can be divided by 2, I can definitely say that n squared is an even number. Then n itself must also be an even number. Let's write that down here as well. N is definitely even. And now this is where the problems begin. What did we talk about at the beginning of the video? In the set of rational numbers, all rational numbers are in their simplified forms. They remain that way. So we said we just wrote something down here. But now I see that both Manisa and Nidhi, the letters M and N have turned out to be even numbers. Since something like this is not possible, then at Hippasus school, that person, whoever it is, could be someone else entirely. They say, well, wait a minute, since something like this can't happen, since both can't be even at the same time, in fact, since all rational numbers are only present in their simplified forms, then it means I can't write a number here in the form of a ratio. Because both can't be even at the same time. As far as I know, this proof was already known in Plato's time. But it is also attributed to the Pythagorean school, and it has been around since those times. So, in this way, the number here, actually the square root of 2, because the sum of 1 and 1 makes 2. Therefore, this must be the square root of 2. Thus, they show that the square root of 2 cannot be expressed as a ratio. And so, with the discovery that there are also numbers that cannot be written as a ratio, look, what did we have in our hands now? We called them rational numbers in English. That is, it comes from ratio, meaning in the form of a ratio. Ratio means proportion. Numbers that can be written as a ratio. But when it was seen that this was not the case, a negative prefix was added. And thus, irrational numbers or irrationals were born. Thank you for watching. See you in the next video.